All right, welcome to episode 3 of our CompTIA Security Plus certification exam series, where we're going to be covering each one of those objectives to make sure that you nail down that information and are prepared for that test. So what are we going to cover in this episode 3? It's all going to be around the CompTIA Security Plus objective 1.3. So domain 1, objective number 3 here, which is explain the importance of using the appropriate cryptographic solutions. Before we get started on this though, I do want to do a shout out to Bruce. Bruce was not my first donor, but he was my first Patreon donor. Now, I am trying to make a living out of this, and I appreciate all of those donations to help me out. There's several different ways that you can help donate. I'll go over those in the description down below, but right now it's really just more of a call out to Bruce. Thank you very much. I appreciate your support. All right, so what are we going to be covering? We're going to be covering this, explain the importance of using the appropriate cryptographic solutions. It's all about cryptography. I think this is one of the coolest topics. I love cryptography. Cryptography is awesome. I have a whole course on cryptography, and it's just a really fun topic to go over. And boy, I can't hardly see that. There's a lot that we're going to cover through on this one, so it's going to be a little bit longer of an episode, but we're going to talk about a lot of cryptography elements here. So we'll start out with public key infrastructure, or PKI. We'll talk about a few different aspects of it, like a public key, a private key, key escrow. We're going to get into certificates and what certificates look like. Hint, PKI uses certificates. So we'll talk about certificate authority, a certificate revocation list. We'll get into online certificate status protocol, or OSCP, self-signed certificates, third-party certificates, root of trust. We'll get into a CSR generation. We'll talk about wildcards. We'll also talk about encryption from more of a high level here. Protocols, symmetric encryption, asymmetric encryption, different levels. We'll talk about transport and communication, key exchange, algorithms, key length, and then we'll get into digital signatures, salting. We'll just mention tools, obfuscation, and hashing algorithms. So quite a bit to cover there. A lot of cool stuff though. Let's start out with public key infrastructure. So a public key infrastructure is a huge part of how the internet has a level of trust, how it has a level of protection to it. It's not 100%, hey, you're fully protected with this public key infrastructure, but it's a huge step in implementing trust. What do I mean by that? Well, when a user connects to some unknown server out there, like we're doing on the internet, we're connecting to another machine, that's actually very dangerous. You are exchanging information with this other machine, and it really opens up your machine to vulnerability. One of the things that mitigates a huge part of that is this public key infrastructure, or PKI. Now, notice that this is not public key cryptography. Public key cryptography is something a little different. Although PKI uses public key cryptography, they are two different concepts. So what is PKI? Well, it's a framework. It's hardware, it's software, it's services, it's policies, it's procedures. It's just a whole bunch of communication that happens in order to establish this level of trust between your laptop and some other machine. It's what allows us to go to websites and have a certain level of trust. So it's a whole infrastructure. So I'm going to give an example of this. I'm going to pull up my site right here. So this is technosurge.com. And this is my site. It does use PKI, and most of your sites that you're going to visit nowadays do have that. And in fact, what I can do is I can take a glimpse into this PKI and what it is. So I'm going to click on this site information right here, and I see the connection is secure, and I click on that, and I see the certificate is valid, and I open this up. Well, this is the certificate. So a certificate we're going to get more in depth into here in a little bit, but just know that this is part of PKI. Certificates are a part of PKI. I can use it in other scenarios as well, but it's a part of PKI. And what does it do is this certificate right here gives me a level of trust that I'm on the right site, essentially. Doesn't guarantee me that this site is safe and protected or anything like that, except for it just is a level of guarantee that I'm on the right side. Right site. And then also what's happening is we're establishing a TLS connection between my machine and this machine. And so not only that, we have a certain level of confidentiality when we're communicating with this machine. So that's an example of public key infrastructure right there. All right. So what does this look like? Well, first of all, we have private keys. So there is this private public key pair. So the private key is this key that resides on the server, and it's what's used to encrypt the traffic that comes to the end user. So let's say this is the technosurge.com website. It's got a certificate that it passes to this user, and that certificate has a public key. So one of the things that can happen is it can encrypt the traffic with this private key, send it over, and then this user can decrypt it with the public key that exists on this certificate here. And so now there's a certain level of, well, at the very least, I know that this data that is being sent to me is being sent by the machine that has this private key on it. So that's this idea between a public key and a private key. There's also this idea of key escrow. And escrow is just maybe like a holding container. And think of escrow, well, you know, when I bought a house, I had some money that was tied up in an escrow account, which just means that there's this third party holding on to it. Well, a key escrow is just this third party that is holding on to the key. Think of like a lockbox. If I have a bunch of keys and I want to keep them secure, I put them in a key lockbox, and then I change, you know, I have a password to get into it or something to that effect in order to get into those set of keys. Well, it's the same thing when it comes to key escrow when we're talking about digital keys. And there's places and ways that we can store digital keys to make sure they maintain a certain level of security. So that's a key escrow. It's like storage for digital keys. All right, what is a certificate? Well, a certificate is what we exchange back and forth. It has the public key that's on it. And there's certain, with this public key and the certificate, a certain validation that happens of the site that I've reached. And so that it validates the site that I've reached, and the traffic coming from it, it validates that traffic that it's coming from the correct source. So a certificate, and we can actually, once again, take a look at it. This is the certificate. I mean, it's showing you this right here is showing you the certificate for technosurge.com. And we could even take a look at all the details of this certificate and what those look like. So that is a certificate. It's a big part of PKI. We also have a certificate authority. So what is a certificate authority? Well, we have certificate as part of it, and authority is where it comes from, the CA. So we have some sort of source right here that this certificate actually comes through the machine that we're trying to get to, and it comes to us essentially. It gets downloaded and installed on the server, and then when we communicate and connect to the server, then it gets sent to us. So the certificate authority is essentially the one that creates the certificate, and for the most part we can consider it as saying, yes, this server is the correct server, that the information that you're getting came from the correct server. So, and that is the certificate authority. So that's up in the cloud, and we have this certificate authority here. All right, so if the certificate authority creates these certificates, which does the validation of the server right here, what happens if something were to be compromised? For instance, let's say somebody gets a hold of this private key. Well, that's problematic, because if somebody else has that private key, they can send traffic and make it look like it's coming from technosurge.com. And that can be a problem. We can be compromised that way. So what we have is we have a Certificate Revocation List, or a CRL. What this machine does, it will download the Certificate Revocation List. And if there is a certificate that, let's say this private key was compromised, what we do is we report it to the certificate authority and say, yeah, we were compromised. And now it gets downloaded onto the machine. And now when this user sees that certificate, it's going to consider it as a bad certificate. So it's a way to track bad certificates and making sure that, once again, we're not connecting to sites that are going to be untrusted. Now, One of the problems with the CRLs is it's kind of an old system and it is kind of flaky and it doesn't download a lot of times. And so it's not something that is really spontaneous and like it's kind of slow. It's a slow mechanism. So we also have this online certificate status protocol. So notice this is a protocol. What is a protocol? Well, a protocol allows us to do some sort of communication. So it's a set of rules for communication. So what is it? What is this protocol for? It's to check the status of these certificates, and it's to do it in a little more live. So when we get a certificate, we don't have to always rely on that outdated information of the certificate revocation list. Instead, we can actively send a message up to a specific server in the cloud and say, is this certificate is good? And get a response right away and say yay or nay if that certificate is good. So that's the online certificate status protocol. It's a way to verify that a certificate is still good and has not been compromised. We also have self-signed certificates. I mentioned the certificate authority, and what happens is that this certificate authority will create a certificate, but that usually costs money. What happens is that we create a request, send it up to the certificate authority, and give them money, and then they send us the certificate right here. Well, imagine that we have 1,000 different servers, and those 1,000 different servers, the end users are not connecting to these servers. But we do need to communicate to those servers, and they need to communicate amongst each other. We're not going to go and buy 1,000 different certificates to get that all to communicate together. So instead, what we can do is we can create self-signed certificates. Now, the self-signed certificates says, okay, well, when you connect to this, we're going to give you a self-signed certificate. There's not a certificate authority that's going to approve it, that's not the way it's set up, but instead, we're still going to use this certificate. Well, why would you want to use a certificate? Because so far right now, I'm saying that the certificate verifies the server. Well, we know what we're connecting to, but we do want maybe the communication between us to still be secure. We still want to encrypt it. So we still need a certificate that helps facilitate that process. So that's where we do a self-signed certificate. In this case, with a self-signed certificate, it's the server itself that generates the certificate. It sends it, when a user connects to it, then they get that certificate. It recognizes that it's a self-signed certificate and throws up a warning on the machine and says, do you really want to connect to this site? It could be problematic and it could be evil. And it could be something you don't want to connect to. But we know what we're connecting to. We know exactly what we're connecting to. We know that it has a self-signed certificate, and we're going to say, I accept this risk. And now we still can communicate with encrypted channels, but without the need for going out and buying an actual certificate from a certificate authority. There are also third-party certificates. And if we go to a third party like a certificate authority and get a certificate, that's an example of it. This would be a third party. Where are the parties? Well, us is one party, here's a second party, and here's a third party. Those are the three parties involved here. But it doesn't necessarily have to be a certificate authority. Maybe we've partnered with another business and they have their own certificates. And so what we do is we use those certificates in order to help this authentication process. Whatever the case may be, it's just a certificate that comes from a third party. At some point in time, there has to be a level of trust here. So we're connecting to a machine that we don't really trust. But how do we still communicate to it because we still want to communicate? Well, the trust gets passed on from a root of trust. And this root of trust trusts the server, and then it gives it a certificate so that way you can essentially have a certain level of trust in this server right here. So the root of trust is wherever that trust stems from. In this case right here, it's the certificate authority. There are other examples of this. There are other ways that we can trust machines, but this is one of them, is this root of trust. Okay. Then we got a certificate signing request, a CSR, and there's the generation of it. So a CSR is what is going to be sent to the certificate authority so we can get a certificate. So essentially what happens with this process is this machine right here needs to communicate with end users. So it generates a private key and a public key pair. It needs to get a certificate. So what it does is it generates the certificate signing request, which includes this public key, and sends it to the certificate authority. That certificate authority will then generate or create this certificate, which will then get sent back to the server, installed on the server, and now when this user makes a request of that web server, then it gets sent the certificate. So essentially, the CSR is just so that way this server right here can create this request that gets sent to the certificate authority. That's what we send. We send the CSR to the certificate authority. There are also wildcard certificates. So a wildcard certificate is, here, let's use that example again of, let's say we have 1,000 different servers, or let's say technosurge.com. I've got a few different sites. I've got technosurge.com. I got resources.technosurge.com. I've got a courses site. I've also got a member site, and they all have a little different domain, but they all end in technosurge.com. So what I do is I ask for a wildcard certificate, which kind of puts a star at the beginning of this. So now it doesn't matter if that's www, if it's resources.technosurge.com, or if it's members.technosurge.com. It doesn't really matter what it is. It's a certificate to be used for all of those websites. And now I can install that on each one of my servers. So that way, when you connect to www.technosurge.com, you'll get this same certificate as if you were to connect to members, as if you were to connect to resources. It's all the same certificate, but it counts for all of those sites because it's a wildcard. And the wildcard is because that first part can change. By the way, I have a whole course on cryptography, which takes a very different approach. Right now, we're just sequentially going through all of these objectives, which can be a little bit like memorization. Essentially, we're talking about a lot of these concepts without really diving deep into how they all function. This is fine when you're studying for a certification to a certain point. It can get you to pass the certification. This is what actually most certification courses that you get out there take this exact same approach. But it does feel like memorization. Let's say we're trying to memorize this picture, and we don't need to memorize the whole picture. We're just memorizing certain aspects on it because we're only going to be tested on certain aspects on it. This is a great way to become an expert at a test. This is not a good way for retention. We don't retain as much information this way. This is not the best way because there's little to no real world application. And it can be frustrating and extra study time just by solely using this as a methodology to studying. And once again, this is how most certification tests and training, how they operate. But I have a much better system out there. I have a whole bundle that really looks at the real world, looks at the big picture. Now imagine that you're going to take a test that you are going to be tested on specific parts of this picture, but you see the whole picture now. It is a game changer. And my whole bundle, one example of this is I go over this process much more in depth, and I have a whole series of videos that steps you through the process and talks about each one of these components. So this will go way more in depth into that course. So it's all through my TechnoSurge CompTIA Security Plus bundle. I've got a whole course on cryptography where we step through and really learn this stuff and take a look at it from a real world examples and how this stuff operates. But you'll also get my hacking tactics, techniques, and procedures, my architecting security, security operations, and what we are going over right now is just a small component of my exam prep course, which really prepares you to ace that exam on the first time. So something you might want to check out. I've got it down below in the description. All right, let's jump back into this. Encryption. Encryption is just taking data and we are manipulating and changing it so that way people can't really decipher or read it. So we encrypt something. So in this example right here, we're taking the word secret. And the process of converting it into this ciphertext right here is called encryption. We're going to take data, we're going to encrypt it, and people are no longer going to be able to view that. And then we can reverse that. We can decrypt that data so we can view that data or we can use that data. There's really two different types of encryption. One of them is symmetric encryption and the other one is asymmetric. In symmetric encryption means that our keys, and the keys is what is going to code and decode this information. Think of a code and decode, think of locking something in a box and then you can't open it up unless you have a key to open that up. So there's some sort of key to do that. Well, symmetric encryption just means those keys are the same. It's the same key that locks that box as it does to unlock that box. Well, that's pretty simple to understand. But we have this asymmetric, where it's asymmetrical. That means the keys are different. We see there's two different keys here to encrypt and decrypt. And so that's kind of a strange concept that there's one key to lock the box, but there's another key to unlock that box. It takes two different types of keys. So those are the two types of cryptography or encryption algorithms that are out there. All right, encryption protocol. When it comes to encryption protocol, this is what we use to encrypt our communication as we're sending data back and forth. So there's the rules, syntax, semantics, synchronization, all of this stuff that happens to facilitate this communication and to do it through a secure way. So an encryption protocol helps facilitate that communication. We'll talk more about encryption algorithm in a second. I'm just going down the line of all these objectives, so I'm doing it in that order. All right. So when we encrypt data, we're going to encrypt it at different levels. So we can encrypt it at the disk level. So this is a very high level. We're pretty much just saying we're going to encrypt everything. But a disk can be made up of multiple partitions, or nowadays it's probably made up of multiple partitions. So we could encrypt something at the partition level. Now those partitions could have multiple volumes on it, so we could encrypt things at the volume level. By the way, there are some terminology changes depending on what technologies you're looking for. For instance, if you're looking at something like virtualization, then we just call them all volume levels because the physical disk is in the back. So we don't really address that in most of the time when it comes to virtual volumes. Or we could do it at the file level. So what happens is that we store files on a disk. And so everything essentially boils down to being a file on that disk. And so we got a bunch of files. And we can encrypt it at that file level. But those files probably take up many different blocks. So we can encrypt things at the block level. So really all this just means that we can do everything from this very high level, encrypt everything on the disk, to at a much lower level, encrypted at the block level. We can do the same thing with databases. We can encrypt a whole database, we can encrypt a table, we can encrypt a field on that table, or a single record. So we need to choose at what level, and depending on what level we choose, is going to impact maybe performance or how we save and store and how secure that data is. One of the things that we really need to encrypt is when we're communicating. So when data is being transported back and forth, that's one area that we really need to do a lot of our encryption. All right. One of the ways that we do that is that we have a key. It's a shared key amongst the devices. But now imagine that we've never shared a key before. These two devices have never communicated before. So internet is a great example. We want to communicate through HTTPS, through secure communications on the internet always. And really, there should be no exception there at this point in time. There should be almost no HTTP communication. It should all be HTTPS. So in order to do that, we need some sort of keys on both sides. Well, how do we have keys on both sides if we've never communicated with the server before? Well, we go through a process called key exchange. It's a way to figure out a shared key that's going to be on both machines, but do it in a secure manner. And one of the ways that we do this is with the Diffie-Hellman key exchange. The Diffie-Hellman key exchange is a way to exchange keys, and it's really fascinating how it works, but exchange the keys so that way both these devices on each side have this shared key and then can encrypt data that's going back and forth. All right, now we're hitting that encryption algorithm. We talked about a protocol which facilitates communicating securely between two devices, but we also have this algorithm. So what is an algorithm? Well, algorithm is when we take in certain information, process it, and then spit out a result. So it's a function. It's a way for us to take in something, change it, and then spit it out. Well, what are we doing when we're encrypting something? We're doing exactly that. It has some sort of input, like the word secret. It does in this encryption thing, and then it spits it out. Well, encryption, that's an algorithm right there. So we have encryption algorithms, and there's lots of encryption algorithms that are out there. So we call these actually ciphers. So something a little more specific terminology would be a cipher. But we have these different ciphers out there, and some of them are old and outdated, and some of them are new, and we use these different ciphers to help us encrypt data. Well, we actually use an algorithm in a protocol because we need to send data back and forth securely, but we need to encrypt it first. So we'll use an algorithm inside of a protocol. In fact, protocols like TLS 1.3 and TLS 1.2, these are different encryption protocols that we will use. We can actually choose which algorithm we're going to use to help encrypt that data. So algorithms are used inside these protocols. One of the important parts about a key is going to be its key length. The longer the key length is, the more secure it is. And this kind of drives home that point right here. Let's say we have an 8-bit key, which is incredibly small. Like, we don't want 8-bit keys when it comes to encrypting our data. But we've got 8 bits, and if you know anything about binary, that means 2 to the 8th power. That means there's 256 possibilities. Well, what does that mean? That means essentially you have like 256 keys. If a key is 8 bits long, you have the potential to have 256 keys. Well, I could just test one by one all 256 potential keys to figure out which one it is. And at the very most, when I have an 8-bit key, at the very most, I would test all 256 keys to find the right answer. More than likely, I'm going to find a key somewhere in between there. So anywhere from try number 0 to try number 1 to try number 256, somewhere in there, I'm going to be able to crack your code. But you add another bit to that, now I have to try 512 times. If I add another bit, that's 1,024 times. If I go up to 16 bits, that's 65,536. You can see that every time I add another bit, it doubles. And so really, with processing power that we have right now, 16 bits is considered a very low, like a very small key. What a key needs to be is more like 128 bits, maybe 192 bits, 256 bits, 512 bits, and that's for symmetric encryption. When it talks about asymmetric encryption, we need much bigger keys. And so those are much bigger numbers, 1,024 or 2,048, or probably even 4,096 is now what we need to make sure asymmetric encryption remains secure. So it's all about the key length when it comes to encryption. It's a huge part of making sure things remain secure. One of the things that encryption does for us and different cryptography ideas is digital signatures. So I talked about the idea of non-repudiation, that if Susan sends David something and we want to prove that that letter came from Susan, we want to make sure that this is going to be, that it came from Susan and Susan can't deny that. One of the ways we can do that is through digital signatures. And essentially what we do is that same public key infrastructure of taking a document, taking a message, creating a fingerprint out of it, encrypting that using the private key, creates this whole package that when we send it over to David, David can kind of do the reverse of it. I'm not going to get big into the details of how this does this, but essentially does the reverse of it and compares the fingerprints to verify that this document came from Susan, or at least, at the very least, came from the person who has a hold of this private key. And so now David can prove that this came from Susan and also have a certain amount of authenticity or a certain level of feeling like this is a legitimate because it came with this digital signature from Susan. So that is that process for digital signatures. All right, we have salting. Now, there's a few concepts we have to discuss to really understand what salting is. But essentially, when we store passwords in a database, we don't want to store them in clear text. If I was an administrator, I could just go in there and look at all the clear text passwords and then be able to capture those. We don't want our administrators to be able to do that. Same thing if that database were stolen. We don't want somebody to be able to just go and grab all of that information and see everybody's passwords. And so what we do is instead of doing instead of just storing them in clear text, is we do what's called a hash of them, or a hashing algorithm. We use a hashing algorithm. So here I like to use the idea of this blender. We put stuff into it, it blends it, because you can never get that back out. It's not like encryption where we encrypt something and then we can decrypt it. You can't get it back out, but it creates this unique fingerprint. And those fingerprints look different depending on what hashing algorithm that you're using, but it creates a unique fingerprint in which we store inside of our databases. And that's what gets stored. Now, if somebody's typing in their password, all that happens is that gets hashed and then compared against this database. If it compares against this database and it's accurate, then you've been authenticated. So that's kind of the process of how we typically store passwords. Now, the problem is that all I need to do is create a rainbow table where in fact, I got this great lab that does just this, is that we create our own rainbow table. But a rainbow table is just that we've gone through all the possible combinations and created all the possible hashes that there are. And now we just look it up. We look up this number in the rainbow table and we figure out what your password is. So now we have your password. So that's problematic. And so if we're hashing these things, all we have to do is have a rainbow table and we can figure it out. So what we do is not only do we have the password that goes into this hashing algorithm, but we add something called salt to it. When we add salt to it, it creates a very unique fingerprint that's entirely different, and that's what gets stored in this database right here. So now if we have a rainbow table that we pumped in all these possible combinations, it really is not effective if we've used salt. At this point in time, if we've used salt, then it entirely changes this whole table, and so it looks entirely different. Therefore, our rainbow table is no longer functional. And so there are still ways that we can guess a password, but it takes a long time to do that guessing and stuff. So that is salt. Salt is something we add to the password before it gets hashed and before we store it in the database. All right, there's lots of different encryption tools that are out there, things that will encrypt or things that we can use to try to hack encryption. So there's a lot of encryption tools that are out there. We're not going to go over the specifics of that. The obfuscation. Let's talk about some different ways that we can protect data. One thing is we could just not have it. We could put access control on it. We could encrypt it. So one of the things we could do is encrypt it. We could use steganography and we could hide it in things like pictures or other data. We could do something called data masking, in which case, like when you're typing in your password in something, it shows up with little stars, little asterisks. That's called data masking. And then there's obfuscation. So obfuscation is when we take something like a secure word that we see right here, and what we're doing is we're putting hash marks over the top of it to the point where we can't see it. So I like to liken this to like obfuscating code. Some people will obfuscate code where it has a bunch of code for a computer. When you look at it, it's really written in kind of a weird way to make it hard to decipher what exactly it's doing. So that is obfuscation. It's kind of like covering up what exactly it is. So there is several different definitions out there. So this is the most specific, but obfuscation, all of these could be an example of obfuscation as well, depending on which resource that you're looking at out there. All right, hashing algorithms. There are a lot of different hashing algorithms out there. There's ones for like just specifically to hash passwords, and they have certain characteristics that help us hash passwords and keep them secure and safe. There's ones that are just general use, things like the SHA-2 and SHA-3 are general use, and we use it for a lot of different stuff. There are CRCs, which is something that we use in communication and some of the communication protocols. Same thing with the checksums. Some of them we use with storage. And so there's a lot of hashing algorithms that we use out there, and different ones depending on what we're trying to achieve. All right. As I mentioned a few times, that I go way more in depth into this stuff. Like I have a whole course on cryptography. In fact, that bundle that with this TechnoSurge CompTIA Security Plus bundle has 4 major courses as part of it: hacking tactics, techniques and procedures, security operations, architecting security, and cryptography. And it really is designed to give you the skills and knowledge you need to not just be successful at passing the test and not having to memorize a bunch of stuff, but also be able to take the stuff into the real world and actually function with the stuff in the real world. So I do recommend check out that TechnoSurge CompTIA Security Plus bundle. I really love how it all came together. I think you'll love it also. There's labs and there's different exercises to really memorize and get that information down. I take this phase approach where I take more of a global approach, the first 4 classes, where you really understand the material. And then we go into phase 2 and 3. I've got this whole phase system. Phase 2 is doing kind of what you're doing right now, of just like studying really the core test stuff. And then you go into, okay, what is the test actually going to have on it? And how can I prepare myself for what the test is specifically going to be asked? So there's a whole bunch of advantages with going this bundle. I got it down into the comment section. I am going to put a little challenge out here. We talked about this certificate that is on these different sites. So this is my TechnoSurge site. This is the certificate. I'm curious, what is your favorite site? So if you accept my challenge, go out and find your favorite site. Take a look at the certificate information on here, find out when it expires, look through here and find out what the expiration of that certificate is, and come back and report it in the comments down below. And I'm curious to see how many of you, what is your favorite site and what is the expiration of those certificates of the sites that you find out there. So there's the challenge that I have. While you're down there, or even just now, if you could go down there and hit that like button, that helps me out. I can make more of these. If I get more people viewing my stuff, I can keep the momentum of this, make more of them. Also subscribe if you like the series, subscribe and hit that bell if you want to see more of these videos, because I'm going to keep coming out with these episodes. I have about 26 to 30 of them are specifically designed around the Security Plus objectives. So thank you for joining me. It's been fun putting this together. I look forward in seeing you on my next episode, which I'll be releasing soon. So thank you very much.